Hello everyone. Today I'm going to present an overview of our proposed index structure which can efficiently find fair approximate nearest neighbors using threaded B plus trees. And I'm Omid Jafari, and along with my co-authors, this work was done at the New Mexico State University. In general, fairness can be divided into two categories. We have individual fairness and group fairness. The goal of individual fairness is to treat similar individuals similarly, and the goal of group fairness is to treat similar groups of individuals similarly. Locality sensitive hashing, LSH in short, and its variants are very popular approximate similarity search techniques for high dimensional spaces. In our paper, the goal is to improve the performance of finding fair approximate nearest neighbors with regards to the group fairness definition. There are several benefits in using LSH methods for approximate similarity search purposes. For instance, LSH provides theoretical guarantees on the accuracy of the results. Moreover, LSH is a data-independent method, and unlike data-dependent methods, it doesn't need to regenerate its indexes when the distribution of the data changes, for example, in streaming or online applications. Additionally, LSH is known for its ease of disk-based implementations, which makes it very scalable as the dataset size grows. In various applications, there is a need to run similarity search techniques in order to find fair neighbors of a given query and remove discrimination and bias towards specific individuals or a group of individuals. Current LSH methods are not capable of differentiating the dataset points, and they just treat them all similarly. Additionally, changing the current LSH methods in order to find fair nearest neighbors leads to increased I/O and processing costs. There are two naive strategies to change the existing LSH methods in order to retrieve fair results. In our paper, we assume that there are only two groups of points in each dataset, and we leave the option of having more groups for future work. The first naive strategy to find 50% nearest points from each group of points is to simply divide the dataset into two separate datasets and run LSH individually on the two separate datasets. This strategy is not space efficient, first of all, because two sets of indexes need to be maintained. Moreover, redundant processing needs to be performed on the two sets of indexes, which overall results in an increased overall query processing time. In the second naive strategy, we change the stopping conditions of the LSH methods to continue the search algorithm until enough points are found from each group of points. The main drawback of this strategy is that extra and unnecessary data is read from the indexes, which results in an increase in the overall I/O cost. The main reason that in this strategy we are reading extra data is due to the fact that the indexes are not optimized for fairness scenarios, and basically all dataset points are treated similarly. In our paper, we present an efficient index structure for finding fair approximate nearest neighbors using locality sensitive hashing and we call our method FairLSH. The goal of FairLSH is to efficiently find fair top k approximate nearest neighbors in high dimensional spaces without sacrificing accuracy. We propose a threaded B plus 3 structure named FairLSH-Basic that reduces disk I/O, and we further improve on FairLSH-Basic by proposing cost model based structure named FairLSH-Advanced to tune the trade-off between I/O cost and processing time. The main intuition behind FairLSH-Basic is that when enough nearest neighbors of a group are found, we should avoid reading the points of that group from the disk. Hence, our goal is to skip those points that will lead to unnecessary I/O in order to improve the processing time. Skipping the points in the current LSH structures has several challenges that are basically, since hashed points are ordered without considering their groups, when we are reading data from the disk, we might get points from different groups. And the second challenge is that the current index structures only have pointers to the sibling nodes, and there is no possibility to avoid certain nodes of hash functions that contain unnecessary data in the index structure. In this slide, we compare the architecture of one of the state-of-the-art LSH methods called QALSH with our proposed index structure FairLSH. And we use an example to illustrate this. So in the example, the query point is point ID number 2, which is located in node number 1. The white points are from group A and the red points are from group B. And we have two groups in the dataset, A and B. We assume that k is equal to 8, meaning that we want to find 8 nearest neighbors to the query, and our goal would be to find 4 nearest points from each of the two groups. In this example, the original QALSH method will start reading node 1 first and fetching 4 points. It will continue reading node 2, and after that, since the stopping conditions are met, in other words, we already have 8 points, the algorithm will stop. However, we only found 2 nearest points from group B, and therefore the results are not fair. We can use the second naive strategy that we mentioned in the previous slides and basically change the stopping conditions such that the algorithm continues reading nodes 3, 4, and 5. And by doing this, the algorithm finds enough points from each of the two groups. However, as we also mentioned earlier, there are a lot of wasted I/O, and nodes 3 and 4 were unnecessary to read because we already had enough points from group A. FairLSH-Basic tackles these drawbacks by allowing nodes to only contain points from one group, and also by having arbitrary pointers between the nodes. So in this example, FairLSH-Basic starts by reading node 1 and fetching the first 4 points, and now we have enough neighbors from group A. After that, FairLSH-Basic reads node 2 and fetches 2 points from group B. From this moment, since we only need to read group B points, the algorithm jumps to node 6 and reads the remaining points from that node. This way, FairLSH-Basic has saved the I/O cost of reading 3 unnecessary nodes, which are node 3, node 4, and node 5. FairLSH-Basic has a processing overhead in the query phase, which is related to the extra pointers that we have between the nodes. However, this processing overhead is negligible compared to the savings in disk I/O when we have a dense distribution of group points. On the other hand, as it is shown in the bottom figure, the processing overhead of FairLSH-Basic increases when points from different groups are sparsely distributed in the nodes. In this scenario, the indexes will contain more pointers and more bookkeeping is required during the query processing phase. Therefore, when we have dense distribution of group points, breaking down the node and only allowing points from one group to be in the node is a good idea. But when we have sparsely distributed group points, breaking down the node is not a good idea. And in reality, we observe that both of these two scenarios happen in the indexes and in different hash functions. To remedy the drawbacks of FairLSH-Basic, we present a cost-based strategy called FairLSH-Advanced that can smartly detect if breaking down the node is going to positively or negatively affect the overall performance. There are three costs associated with reading a node into the main memory. Cost of disk 6, cost of reading the header or pointers, and cost of reading the payload of the node or the actual point IDs. And the formulas to calculate each one of these costs is included in our paper. So given a node in the indexing phase, the goal of FairLSH-Advanced is to decide whether breaking down the node is going to be beneficial or not. And therefore, we introduce a cost to represent each scenario. As in, we have C before and C after for the cost before and after breaking down the node. And the difference of these two costs can be used to make the decision. FairLSH-Advanced utilizes a user input parameter called theta in the indexing phase. If the C after minus C before of a node is lower than theta, the node will be broken down and vice versa. Also, since nodes have different costs, it's crucial to find a good theta value such that the index will be efficient enough in the query processing phase. And in our experiments, we empirically find this theta value. In this slide, we explain the setup of our experiments. In order to evaluate the effectiveness of our proposed method, FairLSH and its two variations, we compared them with the state-of-the-art LSH algorithms, C2LSH and QALSH. We used two commonly used high-dimensional real datasets and two synthetic datasets in our experiments. The assumption is that there are two groups in each dataset, and the goal of this paper is to give both of these two groups the same opportunity to appear in the final results. Therefore, we randomly assign a label A or B to each data point to represent these groups. And each one of the groups will contain 50% of the dataset. Our goal by proposing FairLSH was to improve performance without sacrificing accuracy. Therefore, we used several criteria to evaluate each method. The total amount of data read from index files, and the amount of data read from index files that was not necessary to find the nearest neighbors we were looking for. Algorithm time is the time it takes to find the nearest neighbor points minus the I/O costs. Query processing time is the total time it takes for the method to return top k results. And finally, we define a fair ratio metric to show the accuracy and fairness of the returned results. The closer this ratio is to 1, the higher is the accuracy and fairness. In this presentation, we only show the results for the criteria in bold, and we refer the viewers to check the paper for the complete results. In this slide, the top figure shows the amount of unnecessary data read from the index files. Wasted I/O happens when enough nearest neighbors from group A, for example, are already found, but the algorithm keeps reading data that belong to group A. And as you see here, the wasted I/O size of FairLSH-Basic and FairLSH-Advanced are several orders of magnitude smaller compared to C2LSH and QALSH. FairLSH-Advanced has a slightly higher wasted I/O size than FairLSH-Basic since it is sacrificing wasted I/O over algorithm time. And the bottom figure shows the time needed to find the candidates. QALSH has the highest algorithm time since it uses non-optimized B+ trees that become significantly larger as the dataset size grows. It is also interesting to note that although FairLSH-Basic and FairLSH-Advanced use more complex tree structures, their algorithm time is still lower than C2LSH and QALSH. This is due to avoiding processing of unnecessary nodes, which offsets the overhead of using additional tree pointers. However, because of the sparse distribution of the groups in the real datasets, the overhead of the FairLSH-Basic is higher for real datasets. And FairLSH-Advanced, on the other hand, has a lower algorithm time than FairLSH-Basic since it's using cost models to optimize the index structures and balance the trade-off between wasted I/O cost and algorithm time. The top figure in this slide shows the overall time required to solve a given KNN query and retrieve the fair neighbors. FairLSH-Advanced is the fastest method compared to the others since its index structures are optimized to significantly reduce algorithm time while increasing wasted I/O cost slightly. And the bottom figure shows the accuracy of all techniques. C2LSH and QLSH have a similar accuracy for all datasets, and FairLSH-Basic and FairLSH-Advanced have a slightly lower accuracy or a higher fair ratio. The reason of this difference is because when FairLSH-Basic and FairLSH-Advanced find enough nearest neighbors of a group, they stop reading and processing points belonging to that group. However, C2LSH and QALSH, continue this process, and get more and more neighbors and return the closest k neighbors at the end by removing the false positives using Euclidean distance calculations. We should also mention that a difference of 0.05 in fair ratio is very small compared to the savings in IO costs and algorithm time. We also analyzed the returned results from each one of these methods for the experimental datasets, and we observed that the returned results or the point IDs that are returned are similar. In conclusion, we saw that state-of-the-art LSH techniques suffer from significantly slow query processing when finding fair nearest neighbors. To alleviate these problems, we presented a novel structure called FairLSH with the goal of improving the performance of retrieving fair nearest neighbors. In FairLSH, we used threaded B plus trees and cost models to overcome the challenges of indexing datasets with multiple fairness groups of data. And finally, we presented experimental results on real datasets to show the efficiency of FairLSH as compared with the state-of-the-art LSH approaches. Thank you for attending our presentation. We hope you'll find the information useful, and in case you want to contact us, this is our contact information. Thank you for your time.